This video will accompany the second half of Chapter 3. Section 3.2 looks at the association between quantitative variables. In the previous section, we discussed how two variables might exist a pattern with one another, but that does not imply that one of the variables directly influences the other. We looked at ways to summarize two categorical variables with two-way tables, a difference in proportion, and bar charts. In this section, we will focus on exploring the relationship between two quantitative variables. How can we visualize the relationship between two quantitative variables? To illustrate the visualization of two quantitative variables, we're going to look at a data set from brickset.com, which is a website dedicated to information about Lego sets. The website includes information about different Lego sets, including the number of pieces, the number of minifigures included, recommended retail price, price per piece, and set type. We're going to focus on the variables recommended retail price and number of pieces. Take a moment and look around the website. You should see that the website is not very easy to navigate. Gathering all the information about each set would be difficult. Luckily, someone else has already done the work for us and provided this plot. The plot gives us a quick way to see that as the number of pieces in a set increases, the price of the set increases. Plots like the one above are known as scatter plots. A scatter plot is a plot which represents the data from two quantitative variables as points. Each point on the plot represents two values, one from each of the quantitative variables. The explanatory variable is located on the x-axis and the response on the y. To illustrate the scatter plot and how they are constructed, we're going to look at a small part of the Lego data. We're going to focus on the 7 sets from the Dino collection. The data is given here. When creating a scatter plot, the first thing we need to do is decide which variable is the explanatory variable and which is the response. In this case, it is reasonable to think that the number of bricks in a set will be able to predict the suggested price, so the number of bricks will be the explanatory, and the price in dollars the response. To create the plot, we start by drawing the x-axis. Notice that the number of bricks range from 80 to 793. We want to place tick marks below the x-axis equally spaced so that we have enough values to cover the range of the number of bricks. For example, we could have the following. Next, we want to do something similar for the y-axis. Notice that the price range from 12 to 100. We want to place tick marks next to the y-axis equally spaced so that we have enough values to cover the range of price. For example, we could have this. Now we can add points representing each of the sets from the Dino collection. Looking at the first set, Ambush Attack, notice that the set costs $12 and contains 80 bricks. We want to place a dot where $12 and 80 bricks intersect. The plot below, or this plot rather, illustrates this point. From here we can add the rest of the data points and a title. Scatter plots can be created by hand, using an online app, or with any statistical software. Looking at the plot, we can quickly see that as the number of bricks in the set increases, so does the price. Notice that by describing the relationship we see in the plot, we are describing the association between the number of bricks and price. Recall from earlier that two variables are associated if values of one variable exhibit a pattern with values of the other. So how can we describe the associations that we see in scatter plots? When describing the associations between variables in a scatter plot, there are 3 characteristics we need to consider: direction, strength, and form. We can describe the direction of an association as follows. A positive association means that the values of one variable tend to be higher when values of the other variable are higher. In this case, the scatter plot will go up and to the right. Notice that these 3 scatter plots exhibit a positive association. A negative association means that the values of one variable tend to be lower when values of the other variable are higher. In this case, the scatter plot will go down to the right. These 3 scatter plots exhibit a negative association. Two variables are not associated if knowing the value of one variable does not give you any information about the value of the other. In this case, the scatter plot will have no pattern. The 2 scatter plots on the left are not associated, or have no association. Looking at the plot of the Lego data, we can see that the plot goes up and to the right, Therefore, it is a positive association between the number of bricks in a set and the price of a set. We could also describe the strength of an association. When the points are clustered very close together along an underlying pattern, we say that the association is strong. So notice that the two plots on the far right are strong. When the points are clustered somewhat close together along an underlying pattern, we would say that the association is moderate. So each of these have a moderate association. When the points are clustered far apart, we say that the association is weak. So here we would have weak associations. Notice that association, we can combine the idea of positive and negative, as well as strong, moderate, and weak, and think of these on a continuum. Looking at the plot of the Lego data, we can see that the underlying pattern is a line. The points are clustered close to the line, so we can say that the association is strong and positive. Associations can take different forms. When the underlying shape is curved, we call the association curvilinear. When the underlying shape is a straight line, we call the association linear. Linear associations are also called correlations. Looking at the plot of the Lego data, we can see the underlying pattern is a line. Therefore, the association is linear. Looking at this plot, notice that the first two are linear, and the third is curvilinear. How can we numerically describe the relationship between two quantitative variables? In Chapter 2, we saw different numerical summaries for a single quantitative variable, such as mean, median, and standard deviation. There are also numerical summaries to help us with two quantitative variables. On page 14 of your notes is the definition of the correlation coefficient. The correlation coefficient is a numerical summary of the direction and strength of a linear association between two quantitative variables. If the correlation coefficient is calculated from sample data, we denote it with the letter R. If the correlation coefficient is denoted from population data, it is denoted with the Greek letter rho. Take a moment and read the information on page 14 of your notes about the correlation coefficient. When you come back, we'll look at page 15 and an example together. Below is a scatter plot which displays the number of abortions performed per 1,000 women versus the percentage of women in a country who live under liberal abortion laws. For example, find the point representing Oceania. Notice that this point is right here. In Oceania, about 75% of the women live under liberal abortion laws, and there are about 15 abortions per 1,000 women. Take a moment and pause the video and see if you can answer these 5 questions. When you come back, we'll look at the answers together. Based on the plot, what are the explanatory and the response variable? When we look at scatter plots, the explanatory variable will be along the x-axis. So in this case, our explanatory variable will be the percentage of women living under liberal abortion laws. The response variable will be listed on the y-axis, so in this case, abortions per 1,000 women. If we want to give the percentage of women living under liberal abortion laws and the number of abortions in South America, we need to identify the South America point, which is right here. Notice, moving along to the y-axis, we can see that that is approximately 32, 33 abortions per 1,000. And for the percentage, we have approximately 11 or 12%. Describe the direction, strength, and form of the association in the plot. Well, notice here that this is a negative association because we're going down to the right. Its strength is moderate or weak because the points are fairly far apart from that line, and the form is linear. Based on the plot, is there a pattern suggesting as the percentage of women under liberal abortion laws increases that the number of abortions decrease? Well, yes, we can see that pattern looking here, but can we conclude that liberal abortion laws are causing the decrease? Why or why not? And the answer here is no, because we can never conclude any kind of causation no matter which plot we're looking at. And again, that's because causation can never be determined based solely on a plot. Next, we're going to look at section 3.3, predicting the outcome of a variable. So again, we're going to revisit our LEGO data set. Suppose that LEGO is going to release a new set named Pterodactyl Terror. Pterodactyl Terror. And you know that the set will contain 259 bricks. The question is, can you predict the price? Notice that the set Raptor Chase, if we go back to our data set here, also has 259 pieces. It is reasonable to think that Pterodactyl Terror will be priced around $30 since that is the price of Raptor Chase. Instead, suppose that the new set will have 530 pieces. Can you predict the price? This time we do not have any other sets with that many bricks. We can use a scatter plot to help us. In order to use the scatter plot to help us, we need a way to summarize the information contained in the plot. When the points in the plot have a linear pattern, we can use what is called a regression line to help summarize the information. A regression line is a line that best fits the data in a scatter plot. It is known as the least squares line. The equation for the line can be written as. Now let's look at each of the pieces of the equation. The hat on the y lets us know that y is a predicted value. When writing a regression line, it's very important to make sure that you have the hat on top of the y. A is the intercept of the line. B is the slope of the line. X is a placeholder for the different values of the explanatory variable. The regression equation can be used to predict y for a given value of x. In the LEGO example, the regression equation can help us predict the price of a LEGO set given the number of bricks in a set. For the LEGO data, our response variable is price. To make the equation easier to read, let's replace y hat with price hat and x with bricks. The regression line becomes this. How do we find that slope and intercept? Well, we'll use a computer to help us finding them. Using a computer, we find that A is equal to 5.61 and B is equal to 0.12. Replacing them in the equation gives this. We can use the equation to help us predict the cost of a set containing 530 pieces by setting bricks equal to 530 and solving for the predicted price. So this tells us that the predicted price for a set containing 530 bricks is $69.21. Now it's your turn. For each of the following new sets, find the predicted price. Pause the video, and when you come back, we'll look at the answers. Were you able to find this predicted price for part A? And this predicted price for part B. Notice that the predicted prices will fall on the line. We can use the plot to predict the price of a set containing 530 bricks. We can do this by drawing a vertical line at 530 bricks. Notice that the vertical line intersects the regression line at 69.21. This is the same predicted price we got using the equation. The line and the equation contain the same information, but the equation will give you a more precise value since the line requires you to look at the graph and estimate the value. So how are regression lines chosen? To find the slope and intercept of a regression line, we need a way to compare the data we observe and the line that we summarize the data with. We need two definitions. The observed value of y is the response value observed for a data point. For example, each of the prices in the LEGO data set is an observed y. The predicted y hat, is the response value that will be predicted for a given x value based on the line going through the points. For example, each of the predicted prices you found on the previous page are y hats. The regression line is the line that makes the predicted value closest to the actual value. So looking at our picture here, we can see if we draw a vertical line going through this point, The y value for this point represents the observed value of y, and the y value for the intersection represents the y hat, or the fitted value, because it came from the regression line. Residuals give us a way to compare the observed y's to the predicted y's. The residual for each data point is equal to the observed minus the predicted. We can also say that the residual is the vertical distance from each point to the line. So in this case, the vertical distance here, that distance is equal to the residual. Take a moment and see if you can answer these 4 questions. Pause the video, and when you come back, we'll look at the answers together. The first question asks, using the LEGO dataset, how many residuals could you compute? Well, to compute a residual, we need observed y's. Looking at our dataset here, notice that there were 7 different data points. Therefore, there are 7 different y's, so we would compute 7 residuals. What is the predicted cost for a set containing 271 pieces? Well, we can use our regression line and substitute in the value x to find that the predicted price for a set containing 271 pieces is $38.13. What is the observed cost for a set containing 271 pieces? Notice that Triceratops Trapper has 271 pieces. So looking at our data set, we can see that the observed price is $50. Computing the residual for this point, what we would need to do is take our observed price of 50 minus the predicted price of 38.13 to get the residual of $11.87. Here is that on the chart. This is that point, and what we're saying is the vertical distance from this point is that 11.87. The goal is to make all the residuals as small as possible. We can do this by drawing the regression line, also known as the least squares line, which minimizes the sum of the squared residuals. We can see this in a picture by drawing the squared residuals on each point. So notice for each point what we've done is we've looked at that vertical distance from the point to the regression line and then built a square around it. Notice that since the squares are connected to the line, if we change the line, the squares will change in size. The regression line is the line that makes the squares as small as possible. You will not solve this by hand. Instead, you'll use a computer or be given computer output. Computer output will look slightly different from software to software. An example of the output for the LEGO set is given here. So notice, looking at this output, the column that you're interested in is the estimate column. Here is the intercept, and then the slope will usually be given by the name of the variable. So this is the A and this is the B that we've been using all along. Regression is a wonderful tool because it can help us predict what will happen when we don't observe every possible value of the explanatory variable. It is one of the most commonly used tools. As with any tool, we do want to make sure that it is appropriate to use. So take a moment on page 21 and read the guidelines for using a regression line. What else can a regression line tell us about the relationship between 2 quantitative variables? The slope and the intercept of a regression line hold valuable information for summarizing the variables. Each has its own interpretation. These interpretations are very important, and you will need to know them for the exam. So in your notes, I would star these different interpretations because you will have to memorize these types of interpretations for your exam. We'll start out by looking at slope. Slope is the predicted change in the response variable y given a 1-unit increase in the explanatory variable x. For the LEGO dataset, in context, what this is telling us is that the predicted change in price each time a brick is added to the dataset is to a 12-cent increase. The intercept is the predicted value of the response variable y if the explanatory variable x is equal to 0. It does not always make sense to set the explanatory variable equal to 0. For the LEGO dataset, it doesn't make sense to talk about the set of Legos containing 0 bricks Therefore, it does not make sense to interpret the intercept for this example. Recall that the correlation coefficient from earlier in the notes. There is a connection between the correlation coefficient r and the slope of the regression line. And it ends up that slope is equal to r times the standard deviation of y divided by the standard deviation of x. There is one more numerical summary of two quantitative variables that we need to discuss. It is the coefficient of determination. The coefficient of determination is equal to the square of the correlation r squared. Some texts will use capital R squared. It tells us the proportion of variation in y that can be explained by the least squares regression of y on x. So if you're asked to give the interpretation of the coefficient of determination, you're looking for that last sentence that I just read. Students sometimes find the definition of the coefficient of determination confusing, so we'll illustrate it with an example. Take a moment and read the example on the top of page 22 in your notes. Computer output, which gives us the regression line, will usually also give the value of r squared. Computer output will look slightly different from software to software. An example of the output for the LEGO dataset is given below. In the output, look for r squared. You do not want the adjusted r squared. So in this case, we see that the r squared for the LEGO dataset is 0.985. Computer output will usually only provide the value of r squared. We can use the value of the coefficient of determination r squared to find the value of the correlation coefficient r. To find r, do the following. Take the square root of r squared, and to determine the sign of r, look at the scatter plot. If the association is positive, r is positive. If the association is negative, r is negative. Based on the output above, we see that r squared is equal to 0.9585. Additionally, we already saw the LEGO dataset has a positive association. Therefore, r is equal to 0.979. This is the same value given earlier in the notes. On the top of page 23 is more information on regression. You can watch a series of videos from Khan Academy. When you visit the link, there are a series of videos on the left which cover different topics from these notes. Section 3.4 cautions analyzing associations. When exploring the association between variables, there are common pitfalls that you want to avoid. We are going to look at 3 of them. Extrapolation is dangerous. Extrapolation is using a regression line to predict y values from x values that are outside of the observed range of data. This is very bad practice. So for example, looking at our LEGO data set, our x values range from a little bit below 100 to 800. We wouldn't want to predict the price of a set containing 1,000 because we don't have any data for a data set around 1,000 number of bricks. We need to be cautious of influential outliers. Outliers can be influential, which means that they have a large effect on the results of a regression analysis. To be influential, the x value is relatively high or low when compared to the rest of the data, and it must fall quite far away from the trend that is shown by the rest of the data. When these two things happen, the line tends to be pulled towards the data point, away from the trend of the rest of the points. So for example, if we look at our number of bricks versus price of a set, if we added a new point that was down here, notice how this new point is far away compared to the rest of the data. If we refit the regression line, we would get the orange line. And notice how this point is having a large influence on the regression line because it would shift quite a bit with the addition of this point. And then finally, correlation does not imply causation. We've already talked about this one, but we have to remember that when two variables are associated, other variables may have influence that association. Another variable that is not measured by the study and influence the association between the response and explanatory variable is called a lurking variable. When two explanatory variables are both associated with the response variable, but are also associated with another, confounding results. So if we think of our ice cream example, if you remember, we saw that there was a clear association between the number of boxes of ice cream sold and the number of shark attacks. But a third variable that we didn't consider was weather. Weather is causing confounding here. When it's hot outside, people tend to buy more ice cream, but people also tend to go swimming more where there are sharks. This concludes the Chapter 3 notes. On the last 2 pages of your notes, or probably the last 3 pages, there are several ways that you can calculate regressions using technology. For your homework, when you need to calculate different regression lines, you can use any of these methods. StatCrunch is automatically located in your homework and is probably the easiest to use.